Today we're going to talk about rational expectations equilibrium, and we're going to use a laboratory. I think of it as being introduced by Lucas and Prescott in their famous 1972 econometrica paper, Investment Under Uncertainty. We're going to use a stripped down version of their model. It's going to have almost everything, but ours is going to be linear quadratic. Okay, so we're going to introduce the notion of a rational expectations equilibrium, which is a really important concept. And the key thing is rational expectations is an equilibrium concept. We want to remember that about. We're going to present this in a very Bellmanized way. So what I'm going to talk about in this little video is a QuantiCon lecture about rational expectations equilibrium. And I've just printed out a printout of the lecture. And then later in the video, we're actually going to go to the QuantiCon site, and we're going to open up a Jupyter notebook live on Colab and show you how that works, using this as an example. Okay, so there's several ways to think about a rational expectations equilibrium. One is as a fixed point, and a fixed point of what? It's going to be a mapping from a perceived law of motion to an actual law of motion. So can I ask, perceived by whom? And that's going to be the decision makers inside the model. So the reason it's going to be a fixed point is the law of motion is going to be partly determined by their own behavior. And so we want to handle very carefully how they take that into account and the step at which they take it into account. So let's go. So another thing we're going to learn about is what's called a big K, little k trick, which is a modeling device widely used in macro. Except for us, we could call it a big Y, little y trick. So we'll see that. Okay, I'll explain this stuff a little later, because a QuantiCon lecture is actually going to explain about the Python that's going on under the hood. So these are kind of Python cells. Okay, so the key thing is in introducing this big Y, little y trick, we're going to describe a model in which a representative firm or a representative agent is a price taker, and we're going to have a competitive equilibrium. So here's the deal. We want the representative firm or the representative person to take aggregate Y, to take big Y as given when it chooses little y. But at the end of the day, we want big Y equal to little y. So when the representative agent is choosing little y, so here, one way to write this is little y is not equal to little y in any way. It's not constrained at all. But at this step, little y is equal to big Y. Or another way to say it is, of course, this is going to be the same thing. Big Y is equal to little y. So how can that be? This is a step that has confused people. So this is kind of the big Y, little y trick accomplishes these two goals by taking, read this, by taking big Y as beyond control when you pose the choice problem of whoever chooses little y, but we impose, key thing is, when we pose the choice problem, we take big Y as fixed, but we impose big Y equals little y after we've solved the individual's optimization problem. So this recipe takes some digesting, and it's at the heart of the concept of irrational expectations equilibrium. And so I'm gonna, for the most part, follow this lecture and do this in a dynamic setting, but Lucas and Prescott did it in a dynamic setting, but the essence of the trick goes through also in a static setting. And I recommend that on the QuantiCon lecture you read section 211, which talks about the static example of the big K, little k trick. Because actually once you understand that, understanding of the dynamics will be pretty easy. So let's go on to the dynamic setting, which in the lecture on QuantiCon website is section 3. So here's what it's going to be. There's going to be a large number of identical firms selling a homogeneous good, single good. Things in action are going to be, PT is going to be the price of the good, YT is going to be the total supply of the good, total quantity of the good, and there's going to be this linear inverse demand function that looks like this. It's downward sloping. It has slope minus A1, and it has intercept A0. So there's this downward sloping demand function. Lucas and Prescott had this thing shifting around with demand shocks. There was a shifter. There was a demand shifter, and it would be very easy for us to add it, but we're not going to do it because we're going to strip things down. Big Y is going to equal little y times n. So there's going to be n firms. And the sense of this is we think of n as a representative or average firm. Okay. And actually, this might seem as a paradox, but the reasoning is fine. Sometimes we set even n equal to 1. You'll actually see that in a lot of applied work. And it's a story or a parable for really having a large number, even a continuum of firms. Okay, so now the firms problem. We'll take the firms problem. Now, according to the rules of the game, firms problem is we have to take big YT as a stochastic, as a sequence. We have to take big YT as given. So the firm problem is going to take big YT as given. So the firm's going to be a price taker. So what the firm cares about, it wants to maximize the present discounted value of its net revenues. And we're going to make this up. Its net revenues are equal to its price times its output. But, and this is what the heart of Lucas and Prescott's paper, there's going to be some adjustment costs of output. So when the firm adjusts output, even raising it or lowering it, it's going to have some costs, which we're going to model as this quadratic function, yt plus 1 minus yt. We're going to square it, divide by 2, multiply by gamma, and that's going to be a cost function. And it's a cost of the change of output. So there's kind of two parameters here. There's a beta discount factor, and there's a gamma greater than 0 governing the adjustment costs. And the whole timing, we're going to assume that the firm observes PT and little y when it chooses yt plus 1 at time t plus 1. So we're going to think of the firm choosing sequentially, if you will. So to make this problem well posed as an optimum problem, specify the dynamics for all the state variables. And these are going to include variables that the firm does not control but cares about. So how are we going to do that? Well, the logic here goes, price, what does the firm want to forecast? Well, it wants to forecast price, but it knows price obeys this demand curve, so that means that it wants to forecast YT. They're connected by a tight linear relationship. So aggregate output depends on the choice of other firms, but our firm's just going to ignore that. It's not going to care what determines it. It just wants to know it. So, so the firm is, the key thing is firms are going to regard our representative firm as aggregate output is unaffected by their own output decisions. That's key. That's our first step. Take YT as given. Big YT is given. That's the big Y. So what we're going to need is we're going to need that the firm believes has some law of motion in order to make its problem well posed. The firm's going to have some perceived law of motion for the for aggregate output. So we're just going to say that, well, what does it think? It thinks this one. We're just going to guess that output is some function h of last period's output. And then we're going to get our forecasts by, what are we going to get our forecasts? We're going to get our forecasts by iterating h of h j times of yt. We're just going to iterate this j times. And that's going to be our forecasting function for yt and plus j. And then we'll just get pt plus j. That's how we're going to forecast pt plus j. That's the way this is going to go. So now we're all set up. Given this, we now have a well-posed problem, and it's going to be a well-posed dynamic programming problem. So we're going to let h be the optimal value function for the firm given h. So v is the optimal value function. So this v, what's the state? It's the little y, and the big Y is going to be the state. V of y is the optimum value of the problem for a firm that has output today of little y, aggregate output is big Y, and the firm is optimizing, given that it has beliefs h about the law of motion of big Y. So if we do a little thinking, the Bellman equation, if you're thoroughly Bellmanized, the Bellman equation is going to be this equation. This is our functional equation. This is price times output. That's price times little y. The big Y got in there because P depended on big Y. That's my adjustment costs. That's my output tomorrow. And and this is my little output tomorrow. So this, we've substituted in the law of motion for y right here for little y. So this is my Bellman equation. It's a functional equation in little y and big Y. And the optimum decision rule that's going to solve that is, we're going to call it little h. So, and look what it's going to depend on. It's going to depend on my output and industry Y output. And HYY is going to equal the, this function is going to equal the maximizer of the right-hand side of this. And then the comment is, evidently, both V and H depend on big H. So now we have, so what we've induced a mapping from big H to little h. In other words, from big this, we've got a mapping. The Firm's optimum problem induces a mapping from big H to little h. Okay, that's the first part. So, so we could actually, I'm going to skip this part. This is technical material which I'm going to skip it, but you're not going to skip it. It's taking some derivatives, and it's getting a characterization of the optimum decision rule using some basically methods in the space of sequences. But I'm gonna come down here, and I'm just gonna jump to the definition, section 3.2, because we're in the spirit of studying rational expectations equilibrium as a concept. And here goes. The rational expectations equilibrium, sometimes people call it a recursive equilibrium, or recursive competitive equilibrium of this model. It's a decision, it's a pair of functions. It's a pair of functions, big H, little h, and big H, such that given H, the function little h is the Firm's optimum policy function, and the law of motion big H satisfies this equation. And where did this equation come from? Well, notice the following. Right here is little yt plus 1 is equal to h of big YT, well, got it wrong, just get the order. It's equal to h of little yt, big YT, that's what h is. We just come back here, here it is. So that one, so that's optimization given big Y, and given the law of motion for Y, actually given the whole sequence for Y, that's optimization for that. And then, so if that's the law of motion for the little guy, what's big Y? Well, big Y is going to be n yt plus 1, and that's equal to n h. I can write this as yt over n yt, and what we can see is, what this implies is that, well, this is yt, and the right-hand side of this is yt plus 1, this is yt, so this is telling us that h of yt must be equal to this. And we want that to be true for all y. We want those functions to be equal. So this is the mapping. This is the mapping from a perceived law of motion. So this is what we want. This is what we want. So in general, it won't be true. If we start off with an arbitrary h, this will not be true. So I'm going to write this down. Not true with an arbitrary h. But a rational expectation equilibrium requires it to be true. So this is a restriction on big H. So the way to think of a rational expectations equilibrium is it's a restriction on an equilibrium object. Three, two, one. This will say it better than I've been saying it. It characterizes a rational expectations equilibrium as a fixed point of a mapping from a perceived law of motion for a market-wide output to an actual law of motion. And we could think of that mapping as being phi. Okay. Now the question is, and this is a question that Lucas and Prescott preoccupied them in their first paper on this. So, how to compute H, the fixed point, that's a rational expectations H. How do you compute that? So here's what's natural. Well, you've seen other fixed point equations in functions, for value functions, say. So a natural thing to say is, well, let's just iterate. Just guess an H. So try this. Try Hj plus 1 is equal to phi. Go through that mapping. H of j, where phi is defined by, what's phi defined by is, phi is defined by, phi is equal to, in our thing, it would be n h y, I could write this out, I don't have to. That conditioned on big H. So this is going to map an H into a new H. So a natural thing would take a guess and drive J to infinity and hope. Well, in general, that'll work sometimes, but lots of times it won't work. So there's examples where those iterations don't converge. So, and kind of the heart of Lucas's original paper was to, Lucas and Prescott's original paper was to come up with a way of computing an equilibrium that didn't iterate on this H. Just make an amendment. There is a literature that started about 10 or 20 years after Lucas and Prescott's paper that went back to iterating on H. We're not going to talk about this. So here's Lucas and Prescott's idea. It was to use some insights that came from the fundamental theorems of welfare economics. So their idea was there ought to be a connection between a competitive equilibrium, a rational expectations equilibrium. That's what they want to know, is what's the connection between a rational expectations equilibrium and a planning problem? Is there any connection? And the answer is there is. There's a planning problem whose allocation, meaning whose YT sequence, is the YT sequence for a rational expectations equilibrium. What we do in this lecture is, this QuantiCon lecture, is we show you that planning problem, and it turns out to be a linear quadratic control problem, a linear quadratic dynamic programming problem. So formulate that and compute an equilibrium allocation, and then, I'm sorry, let me say this. So the way it's going to go, I misspoke in a really bad way. We're going to formulate the planning problem, which is it's a problem only to choose an allocation. We choose an allocation only. So the way we choose an allocation only, and then the second thing is find the associated shadow price and that's going to turn out to be the price. That's an rational expectations equilibrium price. So the way this is going to go is it's going to kind of be a big guess and verify. We're going to describe something called the sum of consumer and producer surplus. So consumer surplus is the area under the demand curve up to YT. So this is consumer surplus. And this thing, producer, is going to aggregate adjustment cost loss are going to be this. So the first is the area under the demand curve. The second is the social cost of changing output. And we're just going to, the planning problem is going to choose big Y. Here's the planning problem. And the key insight is the solution of the planning problem output is a competitive equilibrium output sequence, a rational expectations equilibrium output sequence, and you can back out the prices. And that's what's done here. So I advocate that you follow this this logic that's right here. And then it's going to turn out, it's going to turn out that the equilibrium law of motion for the planning problem is just linear. And the optimum decision rule for the linear quadratic firm within this is also going to be linear. And if you stare at this, this is beautiful. Notice big Y and little y appears in the decision rule for the firm. Okay, so then the way this goes is there are going to be some fun exercises in this QuantiCon lecture, and there's going to be some solutions. You skim through the lecture, you'll see how they go. Okay, I'll say one other thing. This paper right here, this is an extra topic. This revisits and resuscitates the phi mapping. And it's actually as a way to study stability. I'll just say that. But that would be a separate topic. In some ways, it's an advanced topic. Okay, so here's what I want to do. As promised, we're going to have a little fun. We're going to go to, I'm going to take you to QuantiCon and show you how to do something. So I've just gone to the QuantiCon webpage right now. It says lecture, so I push that. I'm going to go to QuantiCon with Python. There's also QuantiCon with Julia, which is worthwhile, but we're in Python right now. I go to the lectures and I pull up somewhere. I'm going to pull up, let's see, multiple agent models. I'm going to go to rational expectations equilibrium, and there's the lecture. Okay, and I see this. That's just what we've been doing. That's the lecture. But here's something that's kind of exciting and fun to do. If you go to the top here, you see the download notebook. See up there? Download notebook, download PDF. It says launch notebook. If I push that button, and I push that at the beginning of this lecture, here's what's going to happen. It's going to take you. It's going to take you to Colab, which it's going to open a Jupyter notebook on some Google computer somewhere on this earth. I don't know where it is, and it's going to start the computer, and it's going to allow you to run the notebook live, and it'll be your own version. You can change the notebook and do different exercises. So it's a great way to do experiments with these lectures and also learn a little Python. So here's the way this is going to go. I've just fired up Colab. You can see where I am up there. I'm at colab.research.google.com. It means I'm on some computer. So this is up and running, and I'm going to push this right. See that? I'm going to push that, hopefully. I'm going to run this anyway. So this is, see that circle going around? That's actually running. It's installing the QuantiCon. It's installing QuantiCon suite of packages on this Google computer. See, it installed all those. It did work. Google's paying for this. Now we go to the lecture. Now it says, let's say we want to start running the notebook. Well, I come over here and I press this again. See where I press that? And I push that again. And now it's going to start the MATLAB. Oh, that was a sin. The Python. I imported NumPy as NP and so on. And now I'm going to import the LQ class. That's a suite. That's a Python object from QuantiCon. That's going to let me do a whole bunch of work. So now I'm all set. I go through the lecture here. And later on, it's going to. I see. Okay. And here we go. So go through all the way here, and there's some exercises here. So here's an exercise, and exercise 1, you're told how to do it. Notice finding the state is an art. There's xt, little y, big Y, and a 1. Find the laws of motion to A and B, Q, R. Do all this. Do that exercise. So now we want to solve this. I'm going to press this again. So I just ran this code. Literally, this ran this code and printed out this answer. So we actually computed a solution. We could do it again. Here's exercise 2. You want to do this? Now, why am I showing you this? Besides it being a lot of fun, and shows you what you can do with this Colab. We can change the numbers here, and you could fire this up, and it's kind of not an excuse to say that you don't have a computer with Python loaded or with QuantiCon loaded, because you don't need one. You just need a browser, and you could, we could edit things. We could change some numbers, like let's see. I'll change this number right here. I'll change that number to 94. Whatever it was. I'll change that and I'll rerun it. So I just recomputed it right there, that fast. So we can do that all day long, and we can have our own versions. So I think that's going to be the end of our lecture today. The key thing about I'm going to go back to this. A rational expectations equilibrium is it's an equilibrium concept. It's an equilibrium concept. And sometime you'll have, if anyone comes up to you and asks you, do you think people have rational expectations? It's a difficult question to understand, because rational expectations is a modifier of equilibrium. It's a notion of an equilibrium where the beliefs about some aggregate are determined by the model. Okay, so thanks for listening.